Okay, so we've been working with our equations of motion. And remember, we have our toolkit for our equations of motion. And that's my change in position is equal to my initial velocity times time plus 1/2 acceleration times time squared. My velocity final is equal to my velocity initial plus my acceleration times time. And velocity final squared is equal to velocity initial squared plus 2 times my acceleration times my change in position. And right now, we're all working in one dimension. We haven't started dealing with one dimension. We're still dealing with vectors. And on Tuesday, we are going to be dealing, or not Tuesday, on Wednesday, we're actually going to start looking at vectors in 2 dimensions. And that will not be on the test, but right now we're just dealing with vectors in 1 dimension. And vectors have direction and magnitude. So right now, I'm going to do a 1-dimensional problem that looks like it's a 2-dimensional problem, but it's really just a 1-dimensional problem. I'm going to try something while we're doing this. See what happens here. Okay, so we've got our vectors in 2 dimensions. We have our toolkit. This is good, and we know that gravity is a 1-dimensional vector. It is an acceleration vector, and it is 9.81 meters per second squared in the y direction. But if I am doing a 1-dimensional problem, so let's take an inclined plane here. And my inclined plane, there's my angle on my inclined plane, and my angle is going to be 14 degrees. And I'm going to have an object slide down my inclined plane here. We're going to start it with an initial velocity of 0. It's going to travel a distance down my inclined plane of, and we're going to make this 2.5 meters. And we want to know the final velocity at the bottom. Okay, that's what we want to know. Well, this is a 1-dimensional problem, but my issue is that my acceleration that I know I have, because I have an acceleration due to gravity, it's not really in that item. So I've got to look at, and I've got to change my frame of reference. So we're going to change our frame of reference. And the reason I'm doing this is I'm doing this to help you out. Oops, there we go. I'm doing this to help you out in 2 ways. One is on Wednesday, we'll start in 2 dimensions, and this is a good way to get us started on the 2 dimensions. The other is I want to go back and look at that trigonometry stuff that we were talking about in chapter 1. Because I had a couple questions about where things were and how problems, how to relate to some problems. So what we want to do is we want to change our frame of reference here. And I will have a part of my acceleration due to gravity that's perpendicular to my plane, and I will have a part that is parallel to my plane. And what we need for this is we need the acceleration that is parallel to the plane. So we want to have that acceleration. Well, we could actually figure that out because we can break this up into its 2-dimensional part. And this is my parallel to my plane here. And it turns out that this angle is the same angle as my inclined plane. Now, the reason I did this as parallel and perpendicular is because we want to go back to our triangle. So now I have my triangle that looks like this. And this is the opposite side. This is the adjacent side, and there's my angle. So if I'm doing my equations, remember that opposite over adjacent is equal to the tangent of the angle. All right. If I know my hypotenuse, the opposite over the hypotenuse is equal to the sine of the angle. So if I'm looking for my acceleration that's parallel, that is going to be the hypotenuse times the sine of the angle. And if I know my hypotenuse is 9.81 meters per second squared, sine of the angle is going to be sine of 14 degrees. My acceleration that's parallel to my plane, which is something that I need to know, would be 9.81 times the sine of 14 degrees. And that's going to be 2.37 meters per second squared. So now I have a one-dimensional problem where I know what the acceleration is along or parallel to my plane, and I can actually work the problem just like I would some other one-dimensional problem. So let's kind of draw our picture again. Remembering drawing your picture is going to be really good. So now I have my acceleration, and my acceleration is 2.37 meters per second squared. We have our initial velocity was equal to 0 meters per second. We did a distance here that we said was going to equal 2.5 meters. And we want to know the final velocity at the bottom. So that's exactly what we want to know. So we go back to our equations here. I know acceleration, check. Time, no. Time I don't know. So that one is not going to help me. This one's got time in it too. So this one's not going to help me. So that one's not going to help me. But this one I have acceleration, check. I have my change in position, check. I know my initial velocity, check. And on my final velocity is what we're seeking. So I know which equation to use. So now I'm just going to do V final squared is equal to V initial squared plus 2 times my acceleration times my change in position. Well, this is 0 because 0 squared is 0. All right. We're going to also go ahead and say that that direction is negative. So now I want to check everything to make sure my direction is negative. So this is going to be 2 times a negative 2.37 meters per second squared. But my change in position is also negative. So I get a negative 2.5 meters. And so I've got that. So my new units now are meters per second or meters squared second squared. So if I multiply my numbers, I get 2 times 2.37 times 2.5. A negative times a negative is a positive, so I've got that. And it's now going to be at 11.85 meters squared per second squared. That's squared, so the square root of that number, I take the square root of my number, I'm going to actually get my answer. And that's meters per second. So now we were able to do a calculation that wasn't in our traditional X and Y coordinate system, because we were able to figure out my acceleration in that coordinate system and we're able to calculate that final velocity. Questions on that one?